So good morning, everybody. This morning we're going to be talking about DIA method design. So actually I was worried that this wouldn't be too relevant at first to people, but I've been getting a ton of questions about how to set up DIA methods, and actually really great questions from people throughout the course about a lot of these topics. So now I'll have a lot of slides that I've been telling people that I would have ready. So there's no excuses for being quiet this morning. I know some people are tired, but I also know that you guys have really good questions about this stuff. So please interrupt whenever you want. So I'm going to be discussing fundamental method design, and one thing that I would like to put forth is this idea that there's no universal DIA method. So I'm kind of going to be talking about a good starting point for a DIA method, but there are things that can change that would require you to tweak your DIA method. So I would caution people from thinking that you can just apply kind of this method I'm going to suggest and just step aside and say everything's good. There are a lot of things that can vary in a DIA method that all need to be optimized. So there's cycle time, the number of injections that you're willing to do for a sample, the mass to charge range you want to cover, so the precursor mass to charge range, the isolation width we've talked a lot about, resolving power, and the AGC target in the case of like trapping instrumentation, or the accumulation time in the case of TOF instrumentation. So the first place I always start is cycle time. So when I'm trying to start to narrow down what sort of DIA method I want to do, the first thing I think about is, what does my chromatography look like? So I'll kind of decide on a particular chromatography setup. This is something that Lucas touched on yesterday very nicely, talking about how he can have a method that has kind of narrower peak widths because it's a longer column and a smaller particle size, or wider peaks. So for this, let's assume, for example, that we have this peak that's 30 seconds wide. Okay, so we know that if we have a cycle time of 2 seconds, that means we get plenty of sampling on this peak. So you can see that we get like 15 scans across the peak. And generally you want to have, I guess the number people will say, between 7 and 10 points across the peak for quantitation. So if we need a cycle time of 2 seconds, let's assume that we're doing this analysis on a Q-Exactive. And on the Q-Exactive or the Q-Exactive Plus, let's say we're scanning at 10 hertz is our scan frequency. So I've put that up here. So if we're scanning at 10 hertz and we need to sample the peak every 2 seconds, that means we can use 20 scans total. Because 20 scans at 10 hertz is 2 seconds. So that's what I've shown here. So if we're covering 500 to 900 with these 20 mass to charge wide windows, that means we'll be able to hit that cycle time. But we've kind of talked about why precursor selectivity is really important, and it's better to have narrower isolation windows. Having these wide windows causes a lot of trouble. So it would be great if I could do 40 10 mass to charge wide windows. But then I would be really pushing it, because now I only sample the peak half as frequently, right? So now I'm down to only 7 scans on this 30-second peak, and of course the peak width is going to be a distribution. They're not all going to be 30 seconds. Some might be narrower, some might be wider. So I would kind of design against, or think about these things when you're designing your method. And of course, sometimes peaks are really narrow. So you might have this peak right here, which is only 6 seconds wide. And in that case, these methods, this 20 by 20 method won't sample enough, and you might have to go to 10 40 mass to charge wide windows. And this would be really challenging to look at this data with 40 mass to charge wide windows. So I would generally caution people against trying DIA if your peak widths are so narrow, at least in this sort of type of DIA. I know like Waters has had a lot of success with their MS to the E method, where they don't do any precursor isolation on the front end, and that allows them to get very fast cycle time on their instrument. So another thing to consider is how many injections you're willing to do per sample. So another example, looking at the same peak, if we wanted to get really great precursor selectivity, like 5 mass to charge wide windows, we would need 80 of them, and there's no way we're going to sample that peak enough. But one thing we can start to consider is say, well, what if I did multiple injections? So this is sort of the experiment I was showing peptide detections from before. If you're willing to do 2 injections, you get greatly improved data, and I'll show some of those improvements, of course, at the expense of runtime and sample amount needed. So if you're willing to do it, you could do 1 injection that just covers 500 to 700 mass to charge, and then a second one that covers the other half. And by doing that, you're effectively able to scan each peak just frequently enough by cycle time, and you've gained this. You've gained in data quality. So it's kind of a slider between number of injections and data quality, which I suppose is something we're already used to with shotgun proteomics. Another thing to consider is what mass to charge range to cover. So I've been showing these methods where we're just assuming coverage of 500 to 900 mass to charge, and we're calling that comprehensive. Like, I had this picture of the Mona Lisa before, and then I showed the DIA kind of just was framing her face. So we're trying to analyze the part of the data set that has the most information. So what I've proposed is to look at the mass to charge range from 500 to 900 mass to charge. So this plot is from an experiment in the McCoss lab that was done by Jesse Canterbury a while back. This was actually done on an LTQ Velos, and what the experiment was is just taking a triptych digest and doing multiple kind of Pacific runs, doing these DIA runs with very narrow isolation windows with 2 mass to charge wide windows. So for example, this run here would have 32 mass to charge wide windows covering 400 to 460, and so on and so forth. And then the plot on the y-axis is the number of peptides from each of these runs. So what I'm trying to show is that, as people have brought up before, is that the mass to charge range has an uneven, like non-uniform distribution of information of where peptides are. So when we're considering what mass to charge range we want to cover to be able to assess the most peptides and therefore assess the most proteins, it makes sense to focus in on the dense region. So this is kind of a plot of that density. And we've kind of done 500 to 900, and different groups will do wider mass to charge ranges. There's trade-offs for and against that. You get more peptides, but possibly lower quality data. But of course, the other groups, we're all very consistent on focusing in around this range. So other groups will do 400 to 1,000, and then other groups might even go further to 400 to 1,400. I mean, it's similar to DDA when people decide what range they want to cover. It's the same sort of idea here. Any questions on this? Okay. So I've kind of harped on this isolation window width thing. So with DDA, 2 mass to charge versus DIA having these wider windows, and we've talked about oops, sorry about that. We've talked about how there's more peptides being co-fragmented, therefore it generates more complex MS-MS spectra, and it creates more interference. And one of the questions earlier was, well, what do the spectra actually look like? And now I actually have those slides. So here's an example of a spectrum from like a DDA run with a 2 mass to charge wide window. So this should be pretty familiar to people. I've just highlighted the peaks in the spectrum that correspond to this particular peptide of interest. This is with a 2 mass to charge wide window, but when you jump up to a 10, we see an increase in the complexity clearly. So we have these gray peaks kind of showing up, and these are, for one, it's a good illustration of why it's challenging to analyze these sort of spectra using our standard database search tools, because there's multiple components represented in the spectrum. And it also explains, the trade-off of we get these very, very busy spectra. So this is 10 mass to charge, and it gets even worse at 20. So we can see that there's really substantial changes between 20, 10, and 2. And this is what underlies everything that I've been saying, and it's been consistent throughout the course. I mean, Bruno has this great plot of showing the different precursor widths and how many transitions have interference, and you see improvements going down from 20 to 10 to 5 to 2. So in my mind, this is where we improve in DIA moving forward in the future, is to be able to have better precursor selectivity as we move on. And I guess the converse statement would be that I would say it's the greatest limiting factor currently. So looking at this now, we're looking at the same peptide But now we're extracting each one of these fragment ions over time. So this is the data from those extracted fragment ions as you would see it in Skyline for the 10 mass to charge wide window. But when we jump to a 20 mass to charge wide window, you can see now all of a sudden we have some interference showing up. So in this case, it's not the end of the world because the interference is resolved by retention time. So we still there's not much overlap here, and it's also only in a subset of the transitions. But this is the easiest way to illustrate the point. There's clearly another peak that's being co-isolated in the 20 mass to charge case, but not the 10. And here's another example that I show that I think I already went over yesterday, so I'll kind of very quickly remind people what it is. It's this co-isolation in this 10 mass to charge wide window of a peptide and its form within oxidative methionine, which are co-isolated and share the Y-ion series on this side of the peptide all the way up to the modified form. So they share all of these exact same fragment ion mass to charges, so no amount of fragment ion resolving power will resolve these two peaks in that case. And that's something we don't need to worry about as much with something like DDA. We only worry about maybe deamidation. So another really good thing to show here is kind of that this happens both ways. So with the 10 mass to charge wide isolation window in this case, this is the same peptide in the same mixture. We've got these sort of clean chromatograms. And then with 20, we now have interference in the actual peak. So now this is going to impact our ability to do quantitation. And zooming in on the actual peak, we can see here that this is the signal for the fragment ion in the part of the peptide without interference. So what we're seeing is that we have, in fact, this doubly charged B16. So you can see the charge state's doubly, and it's right in the integration window. So this is the integration window shown in Skyline. I don't know, I haven't been there at all the tutorials, but Brennan, have they seen the ability to see the full spectra in Skyline? Yes, okay, I see. So this is a feature that I highly recommend people use because it's really useful. It's like if you're looking at this peak in Skyline, you can then click here and then you can click here at your interference and say, well, what's my interference? And in this case, we can see that the issue is we're querying for a doubly charged B16 in this interference area, but we're actually getting signal from a singly charged analyte. So not only is it clear by looking at this retention time signal, but also by looking at the signal in mass to charge, we have interference. Similarly, here's a case where we have now the same isolation window width, but in this case, the difference now is the resolving power that we're using for the MSMS scan. So I've talked about isolation window width, but of course it's also important to have high resolving power on your MS2 scan. So now we're looking at, in this case, interference in the 15,000 resolving power case, but none in the 30,000. So here's what's going on. In the 15,000 case, we're not able to resolve this interfering peak from the true peak. So in 15,000, these two peaks appear to be one. They're not resolved, so the signal is causing chemical noise interference for our particular peptide, and then, or for this particular transition. And in the case where we have 30,000 resolving power, we're able to resolve the two, and well, not completely, but mostly, and that results in cleaner transitions. I also should have shown the example, but one thing that I've been starting to see, which is kind of terrifying, is you'll see these transitions that colute really well with your peptide, but they're actually noise. So they'll colute well, and you'll look, and you need to look and see what the mass error is, which is something Skyline will also show you to be sure that they are in fact true transitions. So what I'm saying is that looking at just the elution profile, while it works most of the time, it's not always the case that just because it colutes, it's not interference. Any questions? Okay. So here's the plot that Bruno showed about the relationship between the precursor isolation window width and resolving power and the number of fragment ions showing interference. So what we see is if we start here at, well, here's the worst, is a 24 mass to charge wide window with 17,500 resolving power. as we go along this way, this is using the same resolving power and reducing the isolation window width. So we see large improvements reducing the width all the way down to 2 mass to charge. So this is kind of if you're looking at the future of DIA, right? As instruments get better, as multiplexing methods improve, we're going to be, right now we're around here, but later on we'll be down here. So we already know that there's a lot of improvement. And of course, resolving power increases as well. So the increases in resolving power is when you follow this box from the back to the front. So in my mind, it's been more important. I've focused more on going on this axis of improving the precursor selectivity. And then, of course, just relying on the instrument vendors to make faster mass analyzers is nice. I've been able to jump from kind of 17.5 to this 35,000. Any questions on that? Okay. Another thing to consider is if you're using isotope labeled standards. So using a heavy and a light with PRM, we're fine because those two, the heavy and light precursor, will never be co-isolated. But for DIA, you have to be very careful. So this might be if you're doing an SRM experiment, you would measure these analytes in separate scan events. So you have no issue of the fragment ions interfering with each other. But let's say for DIA, we have this wide isolation window, and these two peaks are separated by 5 mass to charge. This is the heavy labeled form and the light labeled form. In this case, we have the label on this end of the peptide, and what's going to happen if we tried to use the B ions here, if we tried to use the B ions, they would actually interfere between these two peptides because the B ion series does not include the heavy modification. So in this particular case, for quantification of this peptide, we would have to only be using the Y ion series. That's not too much of a drawback on the Q-Exactive because in the case of looking at peptides, you're going to be using HCD, and largely what you see are Y ion fragments anyway. So that's kind of a stroke of luck. But it's something to keep in mind when you're looking at some of these experiments. You don't need to think about these things when you're doing a PRM experiment, but you do for DIA. And of course, there could be cases where you just so happen with your DIA method to have the heavy labeled in one window and the light in the other, and in that case, you could use the B or the Y ion series. But you might have cases here where you still pull out part of one of the peptides and you still have interference from that M+2. Any questions on that? Okay. So another thing to consider, another variable we're going to look into is AGC target, or maximum injection time. So on these trapping instruments, when people are doing DDA, they're generally optimizing for something a little bit different than DIA. So for DDA, the MS2 scans are used just for identifying the peptide, and for the most part, they're not used for quantitation. I know spectral counting, people use the scans for quant, but I think we've mostly been focusing on using the MS1 filtering for quant. So in the case of DDA, the optimization is for the ability to identify as many peptides as possible with those MS2 scans. But for DIA, we're not just looking to detect peptides, we're also looking to quantify them. So we don't want to scan really fast in DIA if it's at the expense of spectral quality, because the burden of quality is much higher when you're trying to do quantification than if you're trying to just identify things. So people will tend to, for DDA, they'll use a lower AGC target for DDA because it means they can scan faster. You want just enough ions in the trap such that you can get a successful identification on that peptide, and then you want to move along as quickly as possible so you can identify lots of things. But in DIA, it's very important to fill the orbitrap, because when you fill the orbitrap, you have more ions and better signal to noise and better quantification. So we've gone over all of these parameters, and all these parameters influence each other. So cycle time and number of injections are related. Also the mass to charge range covered. So if you want to cover a wider mass to charge range, your cycle time increases. If you want to do a lower isolation width, your cycle time increases. And all of these things are interrelated. So this makes for kind of a mess unless you start to fix some of these parameters. So what I'm going to do is kind of present a good way of kind of working through all these interrelated parameters to generate a somewhat optimal method for what you're trying to do. So I've been showing this 20 by 20 mass to charge wide window. It's also the same thing Lucas showed. He's also using 20 mass to charge wide windows. And I'm going to show the process and logic that made me arrive at that method. And then you can apply that for whatever situation you're in. So the first thing that I'm going to do is I'm just going to assume here that I'm just willing to do one injection per sample. So I want to cover the full mass to charge range in one injection. I'm doing that because I think it's a very common scenario, and this same logic I think will be clear later on how to apply this if you were willing to do 2 or 4 injections for your sample. So let's just start with fixing this parameter that we're only going to do 1 injection for the sample. So the next step is to determine the cycle time that we need to use, and then we'll decide on the mass to charge range we want to cover. And then after that, everything is already decided for us because we've now fixed those 3 parameters at the top, and these parameters are then easy to optimize afterwards. So it's just deciding what cycle time you need and what mass to charge range you want to cover. So as I've said before, on determining the cycle time, it's based on the width of your LC peak. So with narrow peaks, you're going to need a faster duty cycle. So let's say in this case, I'm going to now run under the assumption that I have 15-second wide peaks, and I would like to get at least 7 points across each one. So that means I need to sample the peak at least every 2.15 seconds. The next thing is determining the mass to charge range to cover. So I'm going to go with 500 to 900 mass to charge in this case. It's what I've found to work really well. I mean, you're missing out on some peptides. For example, you might miss out if you're using the peptide retention time calibration mix, you might miss out on some lower mass to charge peptides. So think ahead of time if there's some peptides in particular that are really important to you, make sure you're covering those. Globally, I find that 500 to 900 works pretty well, even though I'm missing some of these higher mass to charge peptides. So what I usually see is I have less peptides per protein, but the actual signal, the quantitative signal for those peptides is better. So it's, do you want less peptides with better signal or more peptides with a little bit noisier signal? So the next step then is to choose what you want your isolation window width to be. So if we're doing 500 to 900 mass to charge, as just a rule of thumb for the reasonable ranges, for the Q-Exactive, I would say you should think between 15 and 25 mass to charge. For the QEHF, generally I say 10 to 25, but really 20 usually. And then for the Fusion, also mostly 20. I guess you can go lower if you want. The Fusion Lumos, I would actually recommend doing 10 mass to charge wide windows. And where I get these ideas for the recommendation is that you have this trade-off of selectivity versus ion counts, and I'll kind of get into that later on. Basically, if you want to, the take-home is if you want to use a smaller isolation window width, you need to be able to fill the Orbitrap really fast. And some of the newer instrumentation is better at that, like the Lumos in particular, than some of the older instrumentation. Okay, so we've sort of determined that we need the cycle time, that we have this particular mass to charge range, and we have 20 mass to charge wide isolation width. So now I just do some math to decide at what rate do I need to acquire MSMS spectra. So we know now how many MSMS scans we have in our cycle. It's the mass to charge range we're covering, so 400, divided by the width of the isolation window. So that brings us to 20 scans. Did I just click this? No. That brings us to 20 scans. I always like to put in a single MS scan into each cycle. So in this case, every 20 scans, because the MS1 data gives us a lot of additional information for verifying, gaining confidence in peak detections, for example. So if we assume 1 MS per cycle, that's 75 milliseconds roughly. So the amount of time we need, the speed at which we need to acquire MSMS spectra is we have 2,000 milliseconds for our cycle, and then I remove the 75 milliseconds we're going to use for an MS1 and divide that by 20, which means we have 96.25 milliseconds per scan, and we need to scan at 10.4 hertz. So we know how fast we need to scan, so the next question is, what resolving power should I use, and what injection time should I use? And what's cool on these trapping instruments is that it's pretty easy to find the optimal once you've determined how fast you need to scan. So this is a plot showing how fast this is a Q-Exactive HF, showing how fast the QEHF scans. So that's on the y-axis. For various, each line is a different resolving power, and the x-axis is the injection time. So if we look, for example, at 15,000 resolving power, as the injection time increases, our scan rate decreases because we're taking more and more time to fill the Orbitrap. If we look at 30,000 resolving power, it's the same thing. As the injection time increases, the scan rate decreases. But there's this flat line in the beginning. Does anybody have any idea why that's there? The flat line in the beginning on a Q-Exactive? Yes. So it's due to the transient time. So on the Q-Exactive, there's two things going on at once. You have, while you're measuring your scan, remember this will take like 32 milliseconds for 15,000 resolving power, but for 30,000 it'll take 32 milliseconds. So you're sitting there and it's doing mass analysis, and as it does mass analysis for 32 milliseconds, it fills up the C-trap for the next precursor. So as it's trapping for the next precursor, it's scanning. So in this range here, the mass analysis speed is the limiting factor, right? So the mass analysis is taking more time than we're taking to fill. And once we get here, we're taking more time, we're holding up the analysis because we're taking longer times to fill. So one take home from this plot is that you never want to be in this regime here, because if you're taking this 20 milliseconds, you might as well have taken 40 milliseconds because you have to wait anyway. But now remember, before I said we need this 10.4 hertz acquisition rate. So now it's as simple as drawing a line on this plot. So we know 10.4 hertz is what we need, and we just follow this and say, okay, so I should use 30,000 resolving power, and my maximum injection time should now be roughly 60 milliseconds. So if we wanted to try to do a 40 by 10 mass to charge analysis, this is kind of going to start to get into this trade-off between selectivity and ion counts. Let's say we wanted to do 40 10 mass to charge wide windows. If we're doing that, we need to scan twice as fast, because our cycle time's the same, it's still 2 seconds, but we need to do twice as many scans in that cycle. So now the reason that becomes challenging is that we only have 17 milliseconds to fill the Orbitrap, whereas in 20 by 20 we have 60 milliseconds. So we've greatly reduced the amount of time we have to fill. We really want to reach 1 million ions in the Orbitrap for good quantitation. So this is why on the QEHF, I've kind of leaned or found greater success with this 20 by 20 mass to charge. And one thing that's also kind of neat about this sort of approach for determining your inject time and your resolving power is this is a upper bound. So the instrument will scan at least this fast or potentially faster, because this is assuming that every single scan uses your maximum injection time. But in many cases, you'll have a very strong signal, and you'll fill very quickly, and you'll be able to be perhaps scanning at an effective 14 hertz for many of the scans. So you'll scan at least as fast as 10.4 hertz and hopefully faster. Any questions on that stuff? And these sorts of plots are available. I know like Thermo's put out these plots. This one is from my ASMS poster, but I've heard some interest in that. So if anybody wants this sort of plot, you can just email me, or I'd actually be happy to just tell you how to make the plot yourself. You can just do it with about, I suppose, 20 minutes sitting in front of the instrument in tune. It's not too difficult to do the experiment to generate the plot. So with those two runs, what I was talking about before, like 40 10 mass to charge wide windows versus 20 10, Here's showing the number of ions that we get into the orbit trap for actual empirical data measured on yeast. So with the max IT being only 17 milliseconds on average, or the median, is that we get maybe 400,000 ions into the trap on average. So that means we're not filling the orbit trap, we're not getting as many ions in there as we would like. So we're giving up the sensitivity from ion statistics, but we're getting greater selectivity. And sometimes that's a trade-off you'll want to make. If your sample is very complex, you might really need that selectivity to resolve out chemical noise. But what I found, again, is that this 20 mass to charge works better because we have enough time now with 60 milliseconds to actually fill the orbit trap. So we're hitting our 1e⁶ AGC target. So we're getting greater ion counts at the expense of selectivity. And I found that in most cases, the ion counts is very important. Any questions there? Okay. Okay, so again, now a recommended starting point. So this, by the way, is published now. This is in Nature Protocols. It's just a protocol describing a lot of these factors actually in much greater detail in sort of this thought process. And it ends up also with this idea of a somewhat optimal method. I just say a good starting point for the Q-Exactive. So it's these 20 by 20 mass to charge wide windows, 1e⁶ AGC target for the DIA. The maximum inject time is set to auto, which actually puts it, I think, at 49 milliseconds. 20 mass to charge wide window and default charge state of 2, and of course having the MS1 scan in there also. And all of this stuff is available in the publication. If you're taking this method and trying to do it on an HF, I would say the change you should make is to increase the resolving power to 30,000 and switch the maximum IT to 60 milliseconds. The fusion, similar to the QEHF, although you would want to use an AGC target of 200,000. And that's just, I think, because the fusion's 200,000 is not the same as the QE's 1 million. They're both using the same orbit trap, so there's something strange going on there. But basically, I've always been recommended to do a lower AGC target for the fusion. And if there's no questions there, I'll move into sort of some more advanced concepts to think about. Okay, so one issue with DIA is optimizing the isolation window placement. So in these PRM approaches, your windows are centered on your precursor. We don't really need to think about these sort of things. But in DIA, the windows are no longer always centered on the precursor, so you can run into issues like this, where this is one of your isolation windows on the left and the other one's on the right, and the boundary falls right in between your peaks. So you're splitting your peak, and not only that, but your monoisotopic mass and the base peak in this case is right on the very edge of your isolation window. And that's something that we would definitely like to avoid. We don't get as effective isolation near the edge of the isolation window, and it's also relying quite a bit on the calibration of the quadrupole to have this red line exactly where we think it is. So one way that people kind of have tried to solve this is to use slightly wider isolation windows, so have a little bit of an overlap. In Skyline, we call it margins on the isolation windows. I actually try to optimize the window placement. So this is another setting you can use in Skyline. It's just a checkbox that says optimize window placement. And what that does is it creates no overlap in the isolation windows. It just tries to put the boundaries of the windows in intelligent places. So we can put these in intelligent places because luckily peptides, their masses have this sort of distribution here with what Muddiman Lab has called forbidden zones in between. So this is a plot of if you took all of the potential fragment ions for a peptide, the singly and doubly charged fragment ions, and you plotted their distribution over mass to charge, what you would see is that there are particular places where you often see fragment ions, But there are these places where you never really see fragment ions. So this is for singly or doubly charged fragments. It would be the same sort of distribution for precursors, except a little messier because you would have triply charged and higher charge states. But we can see clearly that there are places where we don't really see peptide masses. And the reason for that is because of the atoms that make up the peptide. So these all have a near integer mass, which means that we can only build up to, when we build up, we get this distribution of kind of discrete masses that we can make. So it's kind of similar to building peptides with Legos. So if you imagine that you're building a Lego tower, you can't build a Lego tower that's 2.5 Legos tall unless you have like a saw, but you can't build one that's 2.5 tall. So any particular tower that you can build is going to be some combination of these elements, and when because they're all very near to this integer, you're going to get something very close to an integer mass when you construct peptides from amino acids, which are in turn molecules built up from hydrogen, carbon, oxygen, or nitrogen. And that's why the peptides fall into these discrete bins, and it means that I can be careful not to place my isolation windows here, but to place them in between the bins. Yeah. Oh, sorry. How narrow is the? You mean how narrow is the calibration? So this is the quadrupole transmission. So this is showing neighboring 4 mass to charge wide isolation windows. So the way I've determined this shape is I only determined it once, so this is the same shape, like copy pasted left and to the right. But the way you can do it, and I think this happens in some of the thermo calibration routines, but what you can do to measure this yourself is if you just run like CalMix, so just shoot in an ion of a particular mass of charge, it can be like angiotensin, whatever you want, and then define a 4 mass to charge wide window and just slide it over your analyte. So like your method would just be a bunch of targeted MS2s of like stepped by like 0.1 mass to charge. And then if you look at that signal over time, you'll see what the shape of your isolation window is. So this is the isolation window shape on a standard Q-Exactive. So this is, and this is the isolation window shape on the Q-Exactive Plus, or I guess in this case the HF, but it's the same quad, it's the segmented quad. So depending on your instrument, this is more or less of a problem. So on the original Q-Exactive, they had this transmission where you're getting lower transmission near the edge of the window than over at the Optima, but they have managed to make this quite a bit better in the newer instruments, and I know SciEx has always had very, very good transmission on their very flat, even transmission on their quad as well. But at any rate, even with this pretty flat transmission, we want to avoid having things at the very edge of the window. Any other questions on that? So yeah, I'll just skip this one.
That slide. So there is some signal drop off. What's the width of that signal drop off there?
Oh, what's the width of the drop off here in the edge?
Yeah.
So it's about a half mass to charge.
It is. Okay.
Yeah, so you have to be careful with it. Yeah, so you really want to be careful to avoid having too many things that are on the very edge. So it would be kind of crummy to have it like say right here. So this point right here is -10, and this point here is about 0.5 away from it. So it's one thing's bad and one thing's really bad. It's bad if you have a peptide here at this 0.5, but as long as it's consistently isolated there in every scan, you can still do quant just fine, like relative quantitation, as long as it's consistently at this point. But if this point moves around at all, if the calibration on the quad varies, that means in different scans or different analyses, your peptide might be isolated slightly to the left, and you'll get this reduction down to like 0.3 0.3% efficiency.
But Jarrett, are you also worried about because earlier you showed using the shape of the MS2 isotope distribution as kind of a orthogonal information, and if you don't isolate the whole envelope, so say if it's split across,
Yeah.
right, then the MS2 isotope envelope looks a bit funky, and then it's harder to use that information, right?
Yeah, so you can, right, so what can happen is you would split the isotope distribution and you would isolate just the M peak, for example, and if you looked then at your fragment ions, if you just isolated the M peak, you would have this distribution where you would only see the M peak in your fragment ions, versus if you like just isolated the M+2 or M+3, you would get a really wonky looking distribution. You would have an M peak, but the ratio would be off.
So are you putting a margin these days or not? Or
No, I haven't been, but it's I mean, it's I don't know why I don't actually. I might as well. to be honest with you, it's not a terrible idea. I've actually just started. I've just started doing this thing where I generate these like automatic reports from DIA, and I have these really nice data sets now where I can look at, say, thousands of peptides and show myself how often does this happen that you're near an edge, and it happens more often than I would like, and that's because this issue, when we were doing 20 mass to charge wide windows, I was like, oh, who cares? Like, that is a relatively small percentage of things because your window widths are pretty wide. But when you start getting down to like 10 or 5 mass to charge wide windows, you have twice or 4 times as many edges, so this happens a lot more frequently. And it's a similar problem with these multiplex methods that I'm using. So it's now more of an issue when we have more advanced instrumentation that can get down to 10 mass to charge, or with this overlapping multiplexing down to like 5. So you actually run into this case a lot more. So it's definitely started to become more of a concern.
Okay, so this is another quick, and maybe we've got all the experts in the room. We can maybe answer this. I always wondered, the original swath paper, describes the margins, but those margins only protect you from signal drop-off. They don't actually protect you from splitting the isotope distribution.
Right.
You would have to make the right-hand margin even larger.
If you're trying to get like singly charged peptides, you would have to make it 3 mass to charge wider. Yeah, if you wanted to get all the way to the M+2 peak on the fragment ion. So yeah, mass spectrometry is difficult.
I have a question back to Brandon. So could you add on, or to you, Jarrett, could you demultiplex if you increase the overlapping size? Could you apply your demultiplexing algorithm just on the margins?
Huh. I suppose I could, yeah. Yeah. So I could narrow down just the signal that's within the margins. Yeah, I haven't tried it. Interesting thought, though. It should be applicable. Maybe an offline discussion.
Question. To avoid the separation between the first isotope peak and second one, why is it possible to overlap scans?
Correct, and that is the approach that Ludovic did in his manuscript, where he was defining the swath approach, and that is a very common approach where you add. Normally, your windows would be right next to each other, like I've shown, right? So you have this clean boundary. So what they'll do is they'll extend the width a little, so they overlap a little bit, and that is in fact a very common approach. So in Skyline, the way you do that is when you're setting up your method, you can define what are called margins, which is the extra amount that will be added to either side of the scan. But sort of the discussion we've been having is that even if you add like a 1 mass to charge wide margin, that will maybe get you the M+1 peak on a doubly charged precursor. So at some point you're going to need to add a margin, and it only needs to be on the right side of the window, but you'll need to add more margins if you really want to get the full isotope peak. I've kind of just ignored it and hoped nobody would notice, but I guess the secret's out now. Any other questions on that? Okay. So conclusions are that there's not really a universal DIA method, but I've kind of tried to propose a good starting point. You really want to try to fill the trap for MSMS scans. And another thing that I just only talk about in the conclusions, but is important to remember, is when we're starting to do, people have kind of talked about doing these DIA approaches, and some people have started thinking of it like a discovery approach where you can look at thousands of things. But keep in mind that then your even though you're doing sort of a discovery approach, your QCs really need to be monitoring your chromatography. So for something like DDA, the chromatography is not quite as important. You can get a bunch of IDs with poor chromatography, but with DIA, we really need these good chromatographic peaks. So I would recommend doing a QC that uses, for example, in our lab, we'll look at peptide retention time calibration standards spiked into BSA and do a PRM run on that. And that's how we actually will monitor QC, because then we can see when our peak shapes are getting off or our chromatography is becoming poor. Okay. So this is sort of another example of the wider windows and the interference. We've already been over this. But now I'm going to talk a little bit about these multiplexing approaches that I've worked on. So it seems like people have a handle on DIA, so why not make it overly complicated and talk about multiplexing? So with multiplexing, we actually can fill with multiple different isolation windows in the Q-Exactive. So while technically isolating multiple precursors at once was something we could do on linear ion trap instrumentation, the Q-Exactive was the first instrument where we were able to do this in software. So what we're able to do on the Q-Exactive is, rather than just filling a single precursor, we can actually fill multiple different precursors one at a time. So this is, now I'm going to explain the multiplexing approach that I've developed called MSX, which is kind of a confusing name, but it's a multiplexing approach. And what we're trying to do is measure DIA with just 4 mass to charge wide windows. So from what I've described, it's too hard right now to do DIA with 4 mass to charge wide windows, because we have, in this case, 100 windows in our cycle, and that would take us 10 seconds to get through. So that's a big issue, and we can't really do that. But the way that we've kind of found to get around this is to, for each scan, don't just isolate one window, isolate 5 of them. So I hope everybody's had their coffee, but the first thing we do is, in scan 1, we randomly select 5 windows from this list of 100 of them. And that's what we're going to isolate in the C-trap prior to fragmentation, or that's what we're going to isolate and fragment prior to mass analysis. So we're going to get an MSMS spectrum that is a mixture of precursors from these 5 4 mass to charge wide windows. So we're still measuring 20 mass to charge of precursors total in the scan. It's just that they're from these different windows. And then in the next scan, I'm going to, again, randomly choose from the remaining 96 windows in the list, or 95 windows in the list. And I'm going to isolate those and measure them. And I'm going to continue that process. Eventually, I'm going to get to scan 20, and I only have this particular set of windows that I can look at, that I can choose. So now it's become very easy. I will isolate these and fragment them. So now in 20 scans, I have measured each and every window. But this doesn't help us at all yet, because these scans are all still isolating 20 mass to charge. We have these busy spectra. So why would I ever recommend doing this? And that becomes clear when you go to the next scan cycle. So now we're on scan number 21, and we've replenished this list. And now I do another random selection of precursors, and I isolate them. And this is where we start to see how this can be a powerful approach. So, oh man, it doesn't get highlighted. So what's key between scan 20 and scan 21 is that we have this some of the scans overlap in information. So in common between these 2 scans is this precursor isolation window right here. So if I were to show you these 2 MSMS spectra, you would look at them and you would see very complex spectra, but you would see that there are some fragment ions in common between scan 20 and scan 21. And you would probably suppose that those fragment ions in common probably came from this isolation window, because that's the only one in common between the 2 scans. You're only going to suppose that. You can't guarantee it, but you're getting information by comparing scans to each other, you're getting information about where each fragment ion came from. So if I was really successful at making these suppositions, you could then take this mixed spectrum, which is a mixture of information from 5 windows, and demultiplex it after acquisition down to 5 demultiplex spectra. And so that's what I've done. So when you acquire data like this with this random approach, it's you can define this as a linear system of equations, which I'm just going to gloss over, but you can define this as a linear system of equations that we can solve, and we can actually do this sort of thing where we demultiplex and get the information unique to each spectrum. And here's what that looks like. So this is showing the extracted fragment ions for signal for the data prior to demultiplexing, which is very noisy. In fact, MSX data without demultiplexing is noisier than standard DIA data with 20 mass to charge wide windows. So the raw data is actually worse than before. But after demultiplexing, we can really clean it up. So you can see that we've removed all this. This contains signal from all 5 co-isolated windows. But after demultiplexing, we've just looked at the signal from a single isolation window, and you can see that we've greatly cleaned up the chromatogram, and we've now saved more transitions for quantitation. So this is also a demonstration of the stuff that Bruno was showing, where as you improve precursor selectivity, you have more transitions that you can keep for quantitation. And then I've always shown this example of the co-isolated peaks, the standard one and the one with oxidized methionine. When you use the multiplexing approach, you actually remove the bad peak, because we're able to resolve down to now 4 mass to charge wide selectivity. So you've removed the interfering peak and probably made selecting peaks easier for you, because we no longer have the oxidized methionine being co-isolated. And here's a combination of MSX, which has this 4 mass to charge wide selectivity, to 10 mass to charge wide DIA. This is the signal for MSX versus DIA when you're zoomed out. So this is actually where the improvement for this improved selectivity is really clear when you're talking about finding your peak, so peak detection. So with all this advanced peak selection stuff, we have to calculate this decoy distribution, and it's going to be a lot easier to narrow down your peak when you have less potential other peaks. It's the same improvement you get from better resolving power or better precursor selectivity. And then when you zoom in on the peptide itself, it's pretty clear that we've removed a lot of the noise. So for example, here's a pretty strong other peak, and it's just not present once we've demultiplexed the data. Here's another example, same sort of story. Any questions on this? Yeah. Oh, sorry, I got confused. Okay.
Is this multiplexing helping? Is it working sequentially, or is it done? Can you do 5 windows at once? Because otherwise the fill time gets lower and your sensitivity.
Yeah, it's almost like I planted you there to ask that question, right? So that's a fantastic question, and that is in fact the reason why in practice I haven't been doing a ton of MSX, because the issue was that as you mentioned is that each one of these windows is filled one at a time. So when we're isolating, rather than having like let's say we've decided to do 100 milliseconds of inject time. That's a long inject time. But if we need to isolate 5 windows separately, it would be fine if we're isolating them all at once. We would get 100 milliseconds for each window, but we're not. On the Q-Exactive, we have the quad isolate 1, then the next one, then the one after that. So what we get is this first window is isolated for the first 20 milliseconds, let's say, and then the next window for the next 20 milliseconds, and so on and so forth. And what happens there is we now, since we've only effectively gotten 20 milliseconds isolation time, we have trouble filling the trap. So this is the distribution of ion counts this is published in the initial MSX paper. We're only getting, at best 250, well, at best the median is 250,000, which is filling the trap to a quarter of capacity. So having to fill sequentially is what really hurt us with that approach. And it's why we kind of developed this overlapping isolation window approach in the meantime, which it looks like, unfortunately, I won't have time to get to. But yeah, it's something to consider. You really only want to use this approach if you have like a very complex sample where you absolutely need the selectivity, even at the expense of ions in the trap. And the other case is on the brand new instrumentation. So I've been like really excited on the Lumos, because on the Lumos, the hotter ion source, due to the ion funnel and the different inlet and the better quad, actually makes it so that even with the limited sequential fills, we can still fill the Orbitrap. So that's been pretty exciting, I think. I think it's hopefully going to revive the MSX approach, especially if I can make the demultiplexing faster, because it's pretty slow right now.
Yeah, so my question is regarding peak sampling frequency, because as I understand, you pick the windows random, right?
Yeah.
So then it means that the frequency of sampling per MS range is now not constant anymore, right?
Yes, that's right. It's right. So the reason I actually did random sampling, and yeah, that's just a caveat. Like I kind of just have to live with that, or at least I haven't thought of any approaches that we get around that. So what I did look at is, for example, you can use different design, like you can call it a design matrix, the way you've determined how the isolation windows are selected. And they have non-random design matrices, so like a Hadamard matrix. But the problem is even worse when you use those sorts of matrices, because what happens is you'll have some of the windows will be consistently always perfectly spaced apart, but other ones will be consistently always as far apart as possible in one cycle and then right next to each other, right? So it'll be like the last one in the cycle and then the first one. And that's even worse, because then you can't even use those. Yeah, it would, and it's an example of why the demultiplexing itself is a bit of a challenge. So one caveat of the demultiplexing is I've described these comparing these two scans to each other, these neighboring scans, and they have this overlapping information, right? But when you jump out, it's not always going to be the scan right next to it that has the overlapping information that's interesting. It could be 20 scans later. And right now, the demultiplexing algorithm makes the assumption that the signal has not changed in those 20 scans, when in reality, you've gone through 2 seconds. And the signal has certainly changed. So that results in a bit of like an averaging. It's essentially similar to if you, in signal processing, did like a boxcar smooth on your data. And that's right now what the demultiplexing algorithm does, but that's one of the primary drives right now, is to actually, it's not impossible to make the demultiplexing algorithm aware of the fact that the signal is changing over time.
Thanks.
Ludovic?
Yeah, it's to follow up on the question about the sequential filling of the C-trap. Have you tried MSX on an LTQ? I mean, we discussed this. Then, in principle, you don't have to worry about that. You should be fully optimal for your MSX method, right?
Yes. So, again, it's almost like I planted you there. Oh no, I guess I don't have that in here. So normally, in other presentations, I've followed up with ways to get around this, right? So ways to fix this issue. So one is to have a very high ion flux, but we're really reaching the limits of what we can do there, I think, with instrumentation now. So the next thing to try to do is to figure out how to co-isolate 5 windows together at once. And on a linear ion trap, that's definitely possible. In theory, although in practice it's a difficult process to optimize, because you need to be isolating, when you're isolating multiple windows at once, the parameters that you would use for isolating a window at 900 mass to charge is different than the parameters you would want to use for 500 mass to charge. And when you have to do both at once, it means that one's going to be non-optimal. So that's some of the issues we're dealing with, but if people are interested in that, it's something I would recommend taking a look at Phil Remish's poster from ASMS in St. Louis. That's been the focus of his work, and it's been something that I've been pleased to work on him with, because we're trying to solve this issue, which would allow us to do MSX with parallel fills on linear ion trap equipped instrumentation. So you would do the isolation in the linear ion trap of the fusion, and then just transfer the ions over to the Orbitrap for mass analysis. And there's a lot of other fun like instrumentation tweaks that you could think, if I could build my own instrument, it would really solve the problem. Like, I think you can also use like for example, like time of flight separation. I think I saw a poster on to to do this. But of course, then you run into the duty cycle issues with TOF. But I can go on about that forever. But it's actually time for me to close now. So I would say stop for questions, but we've consistently had questions the whole time. So are there any remaining questions? Okay then. Thanks, everybody.